This is going to be a short stream. You can't see me, but I can see you. I've been setting something up. I've been wanting to do something to work on certain projects. These projects, like, why would I do them? Because they affect my music, partially. The other reason is because there's something in this project that I want to explore, and we are going to explore that, and we're going to discover that together to prove to you that if something weird happens, I mean, it doesn't really matter. Like, I'm trying to work on low noise, ultra low noise technology. That's what I'm doing. And so we're just going to talk briefly about what noise is, how it's made up, how to detect it. We're going to talk a little bit about frequency. I've got frequency sources, generators. I've got an oscilloscope. I have mixers. I have a program that I'm going to use. It's called Reaper, which, since I'm a musician, I know that there are plugins that you can use to analyze um, sounds and that other sound. So um, what I'm doing today is just that really short discussion. I'm going to go into my equipment. I'm going to talk about calibration, and we are going to calibrate the, which I don't know if I can even do it, because the signal that's coming out of the generator is attenuated by 30 dB already, and I'm using let me see what the input value is. You'll see all this in a minute, but I just want to check this. So the input value is actually, well, actually it's not the input value. The input value from the generator, which I don't, because I'm using an O-scope that's got some problems. It doesn't have the quite the correct input value, but it looks like it's reading about 1 volt. So the situation is that, well, this particular generator actually has a high voltage output. Um, so when I match it into it has a 50 ohm output, both high and low. And when I match it into the attenuator, which is also 50 ohms, I don't think there's a problem. There's a little bit of attenuation change, but anyway, it's 30 dB. It's a 30 dB drop from actually that's 2 volts peak to peak. So there's a formula. I guess I might as well go into this right now. There's a formula, and we're going to look for that formula, I hope. So we want to look up log dBV formula. So the formula for, actually I should probably monitor one of these and just make sure that it shows up. I have to shut the video off on my second computer because it has issues. Now I do have a calculator. So we've got whether it's peak, RMS, whatever, it doesn't matter, because the values will they'll cancel once you do the formula. So we've got 2 volts peak to peak, and we're going to grab this calculator. Oops. Does this calculator have a log function? Uh. Oh shit. I don't know what these fucking buttons are. Area, temperature, acres. Oh, it's got a unit converter thing in here. What's this button? We're gonna have to go onto the computer and do it. So the input is 2 volts peak to peak. I don't think this calculator has a log. Yes, it does. And the output, which is going into the mixer, and my scope is really like super sensitive, so it's got stabilization issues. That's 10 millivolt. Oh, come on, damn it, hold still, will ya? It's about 10 millivolts. Okay, so it's 10 millivolts peak to peak. So we've got 2 millivolts. No, we got 2 volts peak to peak divided by 10 millivolts, which is 0.010 volts. We have that number. Wait, that's... Did I do that right? I did. We're looking for a gain. So that number is 200. So now we take the log of 200. That number is this, and then we multiply that times 20. And it says that's a 46 dB gain difference. That's because I've got a problem with the oscilloscope. The values are not, they're not kosher. It doesn't really matter because what we're looking at is the voltage that's coming out of the attenuator, which again, I don't know exactly what that voltage is. All I know is it's low because I've already tested it through the... I mean, it says it's like 10 millivolts, coming out of that attenuator. And when I hook it up to the mixer, because I read about the mixer, so when we look at typical audio signal mixers and stuff like that, sometimes there's a voltage rail, plus 15, minus 15 volts, which has to do with the total amplification of the input signal. Then you've got... Where did I read? Understand those signals in audio gear. So consumer level, line level is 316 millivolts. That, it says here, it's minus 10 dB. So this is called like your dynamic range. The noise floor is supposed to be like around 50 or 60, and your dynamic range is like 40 dB, okay, for us El Cheapo people. Evidently, the pros get 1.2 volts to play with, which increases that, like, multiplies the dynamic range by 4. So mic levels, like if you have a microphone, what comes out of a microphone is like 1 millivolt, 1 to 10 millivolts. I haven't hooked up a mic or nothing. I got my mic connected to my mixer, and I'm not worried about that right now. I'm concerned with connecting my circuits to my mixer to see if we can get nice clean signals into the mixer so that we can look at noise, we can look at different frequencies and that kind of thing. Um, so consumer line level minus 10 dBV, but it doesn't really tell you. So the difference between level units between R and minus 4 is, you guessed it, 14 dB. Well, the actual difference consumer level is about 11. That discrepancy is due to differences between the measurement standards, etc., etc. And now they're talking about analog and digital. We don't need to get into that. So 0 dB for the pros is 1.228 volts. For us consumer, 0 dB, I thought it was it was 700 and some odd millivolts. And I don't see the answer that I'm looking for. Oh yeah, minus 10 dB is 300 millivolts at 10,000 ohms. Let's go here and look at this. Okay, so we're looking at this. Black is the line level for Pro. 0 dBu reference levels for Pro is the blue line. 0 dB reference level for consumer is the red line, which is 1.414. That's peak to peak. That's peak voltage. So the decibel voltage range for 1 volt RMS is 0 dBV. 0 dB is the AC voltage required to produce 1 milliwatt of power across 600 ohm impedance, which is approximately 0.775 volts RMS. Expressed in absolute terms, a signal at minus 10 dB is equivalent to a sine wave with a peak amplitude of approximately 0.447 volts, or any general signal at 0.316 volts, root mean square. Voltage RMS, a signal at blah 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 blah. Peak to peak, sometimes reiterate, etc., etc., etc. For instance, the peak value, etc., etc., etc. Consumer audio minus 10 dB is 0.9 volts peak to peak. At minus 10 dB. That's pretty high. Oh, and there's another situation too. I'm looking at the DC output, and I want to see if the DC output line out usually present a source impedance of 100 to 600 ohms, etc., etc., etc. Minus 10 dBV. The frequency response of most modern equipment is advertised 20 hertz to 20 kilohertz, which corresponds to the range of human hearing, etc., etc., etc. That's something we can test. Line input. We are connected to a mixer, which goes into a. Is that a line input source? I mean, it connects to a microphone jack, an RCA type jack. But that's considered a line input, though. Where's my flashlight? Usually that's a microphone input. No, it says line right on there. They're all line inputs, those RCA jacks. So, for a consumer, which is us, minus 10 dB is going to be 0.894 peak to peak, and I'm putting in like 10 millivolts right now. That's like a tenth. That's peak to peak too. That's like really small. So I don't know exactly what's going on there. That's that story. So if I jump to my Reaper program and what we're going to do is I'm going to open up Reaper, which is already open. Then I'm going to go into the program and see, that's why I had to frig with that. Might as well just do this now before I do my drink. What the hell? So I'm going to turn on the channel that I'm using in Reaper. Now you can whoops. You can hear me talking, which I'm not sure exactly why I'm hearing myself. I think it's because of wait, am I listening to the input? I shouldn't be. I'm not listening to the input. My line input is set at 80. What if I turn this off? Wait. Test 1 2 3. Test 1 2 3. Okay, I don't know. I'm having to do this by hearing myself. So anyway, it's turned on. My mic is turned on, obviously, because I'm talking through here. And there's a level of noise. So I'm going to bring up the mixer program. And now I can't see it. How do I do that? I'm gonna bring this up over here. It's just kind of confusing with OBS. So Reaper, what is that? It's gonna be this one. Okay, it's a little bit out of place. I gotta have Reaper up, and I can't. You can't see everything. Oh, it's the white background. Oh, it should be right in that corner. And it's supposed to take up the whole field, which it almost does. So what we've got here is I hate hearing myself talk, but there's nothing I can do about it right now. We're going to enter a tone, and that tone is coming from my setup, which I could actually bring up my camera here. So I gotta get rid of this headset too, because it's bugging the crap out of me. I'm just gonna set this over here. So what you see here is what you get. No. You can't see everything. So this is the attenuator, and this up here is a frequency counter. You can see the number as well. Nothing's perfect, but it's working. Over here is the oscilloscope, which monitors the looks of the waveform, the level, and everything. Here, you can't. The top one is a signal generator, and this bottom one is another signal generator. This one down here is a square wave, variable square wave type generator. And what we're going to do is we are going to create certain types of circuits. As you can see, I've got a lot of this stuff here. Some of the stuff I don't even know what it is. Those circuits are going to be used to set up noise experiments. And there's one particular task that I've been meaning to do for like 20 years. I'm talking seriously. 20 years I've been wanting to do this, and I'm going to do it. And it's just one thing. But before we actually do that task, we got to talk about. We have to talk a little bit about noise, and get into all that good stuff. All right. So now what I'm going to do is we're going to get rid of the video camera. And we're going to bring this back into place, which should be right about there. Yep. I mean it fills up the whole picture. That's my OBS getting in the way. And so what we're going to do is I'm going to shut the mic off, and what I'm going to do is I'm going to select frequencies. And we are going to use this, I'm calling it an N-band filter. It's actually Reaper's equalizer thing. And what we're going to do is we're going to maximize the output of one frequency and filter out everything else. That's why this is like a 4-channel parametric equalizer type thing. And there's actually... each one of the numbers represents a pole. It's what's called a pole, and it defines the shape of the wave around whatever it is you want to listen to. That's all those. And I can just manipulate those by grabbing those dots and moving them around. Now the other thing is that this information that's coming in here is digital. It's converted from audio analog to digital, I believe. I'm not 100% sure, but hey. So what we want to figure out is we want to figure out if we can figure out where the input level is on this display that matches the input level that's going into the mixer. And there's problems with that because there's the line level input setting of the computer. There's this thing is actually going through two mixers. It goes into one mixer, then there's actually even an equalizer that's in there. And then it goes into another mixer where I go from that mixer to the... And the reason for that is because my microphone's connected to the main computer, which I have set up right now. And as a side note, when I do my music, I have another computer on the same computer. It's a different drive. And then I use that one. I use that one. I'm going to get this out of the way. I use the music computer to do just music. So we're going to play with this, and I'm going to, maybe you can kind of figure out exactly what I'm doing. We also want to test, you can see on the filter itself, let me just make sure this is streaming, that there's a range on the bottom, and this is a log scale on the bottom, so it goes 50, 100, 200, 300, 500, and 1,000. Then it goes 1,000, 2,000, 3,000, 5,000, 10,000, 20,000, and then it goes up to like 22 or whatever that last number is. I can add a new band. Analyze the slope 0 dB per octave. What if we changed this? 3 dB per octave is a standard slope. So I don't know exactly what that's all about. So
So
here we
here we
go.
go.
The test stone that's normally used is
used is
1
1
kilohertz.
kilohertz.
Um,
Um,
so what
so
you're
what
going
you're
to
gonna
hear
hear
is,
is,
and
and
I've got
I've got
two.
two.
I got
I got
two.
two.
I hate
I hate
listening to
listening to
myself.
myself.
I got
I
two
got two
frequency
frequency
counters,
counters,
both of
both
them
of them
red,
red,
pretty much identical within.
within.
Let's
Let's
see,
see,
100 hertz, 10 hertz, 1
1
hertz,
hertz,
like plus or
plus or
minus
minus
1
1
hertz.
hertz.
The
The
generator
generator
that I'm using now,
it's
it's finally warmed up.
well,
Well, it's still a little bit. It's like plus or minus. It's not very stable. We're gonna look at both generators and see if we can figure out some stuff. Calibration is what it's all about. All right, I'm
Alright, I'm
going
gonna
to
shut
shut this mic off, and
and
we're going to
turn
turn
up
up this audio.
This is
This is
gonna
going to
be
be
fun.
fun. And as you can see, there's the noise floor, and then there's the peak of that signal. That's the signal to noise ratio of that particular signal. Um, and it doesn't. I'm not allowed to like grab something to measure that with. This is minus 6. It's like 4 dB of gain, which is it's really low. But that frequency is very annoying. So yep. We better plug your ears. Is all I can say. I got my headset on, by the way. So I got no way to measure the level. Let's see if we can get a flat response and do like a frequency test here. So this particular filter drops out the hum noise and filters out the lower stuff. So we could probably just change the frequency and watch what happens with this. The higher frequencies on this are minus 18 dB though. That's low. Like it's not amplifying those frequencies very good. Okay, that's a flat response because it's flat all the way across the 0 dB line. So what we want to do is when we change this frequency, we want to make sure that the level does not change across the band. And what that does is it will tell me the responsiveness of my audio, my sound card, and all that good shit. So we can actually turn the level down. This is saying that level is 0 dB. But here So the yellow line is the input. Um, it's the input level. And if I drop that, if I drop that main thing, that just tells me the output level. So I'm concerned with the input level. And you can see that the signal tone doesn't change when I change this. So that's looking at the input level. So I could even do this without having to listen to the noise and that tone. So we're going to set that peak at 0 dB, and then we're going to change the frequency and watch what happens. Wait. Oh, am I on the right thing here? There's some harmonics in there. I was on the wrong input slider. So what I can do is I can actually what the hell? I can crank on the well, wait a minute. No. That's the input to the audio card. And you can see there's some harmonics there. Now, those harmonics could be the product of the computer, or they could be the product of the generator. And so we're going to test that because we've got another generator. We're going to test two generators. All right, so I'm going to turn my mic off, and we're going to set... We're going to set the input level to 0 dB. Well, actually, I could just wait. Yeah, I don't know why it does that. You can see that there's a drop off in that signal level. So I'm going to look at the output of the generator and see if that changes while I change the frequency. And that's matched to the attenuator. So we're going to find out what's going on with that. The other thing that I forgot to mention is we're supposed to use a frequency of 1 kilohertz to do this test. So we're going to change it to 1 kilohertz, and is going on here? Am I hearing this? Why am I not hearing this? Oh. Hello? Hello? Ow, damn it. Fuck. Hello? Hello? Right, so we have to change the frequency to 1 kilohertz and then do the test plus or minus 1 from 1 kilohertz. Because I started out at 5 and we need to be at 1. So that's what we're going to do. The high frequency response is a little bit higher. It's like 1 to 2 dB. It goes up kind of gradually. The low frequency response goes down a little bit. So but all in all, you know, that's where your filtering comes in. You can adjust your equalizer and all that stuff to make those other good things happen. And it could be a product of the equalizer that's on my mixer as well. But I'm not going to change anything because we're just going to change the generator and see what happens. So now the only situation is those two harmonics. Um, they're showing up in both generators, which tells me the harmonics are coming from somewhere outside of the input source. Now, I'm going to set the equalizer to flat. I'm going to set this frequency. You know what? Let's see, what is that? So basically, what I'm doing is I'm calibrating. Um, the bottom oscillator looks like it's working a little better since it's warmed up. And I'm gonna take the equalizer. There's an equalizer where a lot of my stuff from the outside, like the guitar, the piano, and all that other stuff, it's not flat. So I'm gonna set it to flat, and we'll run the same test again from 1 kilohertz. The owl is hooting outside. So there's a 3 kilohertz harmonic. I'm not sure exactly what's happening with that. Um, that owl is out there hooting. You think you would have found his mate by now. And my equalizer is set to flat. Let's do something with this equalizer and see what happens. So I was able to figure out that the fourth equalizer knob could be causing a problem. It's a cheap mixer anyway. That's what it's doing. It's adding some shit in there. But it's okay. What are you gonna do? Nothing's perfect. We're just calibrating to make sure that we can see the frequencies, we can see harmonics, we can see that the response from 0 to 22 of my test equipment is pretty good. It's about the same for both generators. No big deal. So when I do my noise test, I can get I think I can get fairly accurate readings from this. So that 0 dB level, whatever that was, Well, it's actually set. It's set on both of those general. Well, the other one is not. Well, actually, the amplitude is on both of them. It's set to that 0 dB on that graph. Which it just seems like it's very low. And it could be because my input level to the computer is set at 80 dB, I think. Can I hear myself? I want to hear myself talk. Let me just go. I'm gonna just go look at sound control panel real quick here. Oops, wait a minute. Hello. Wait. Yeah, let's make a lot of noise. Let's see here. It's set to 80 because I didn't want a lot of extraneous noise coming into the computer. Oh, good lord, what the hell? It's set at 96,000 hertz studio quality. Damn. It's got audio enhancements enabled. Shit, I can't hear myself. What the fuck? Hello. Fuck. I think my sound just died. Oh, there it goes. It just came back. Alright, good. So now I've got it set to 16 kilohertz, 44.1 kilohertz, 16-bit. I'm gonna run that test again real quick. I don't need this. We're gonna set it at 1 kilohertz. Honestly, this wasn't much of a stream. I can't hear myself though. Why is that? What the hell happens? We turned it on. Hello? Come back, desktop. What the hell? Wait, you guys can hear me, but I can't hear me. So, anyway, it tells me that my equipment is pretty good. There's no extraneous sounds coming from the equipment to the computer. That's all good. Oh, I know what we're gonna do. I can't hear myself for some reason. It's because of OBS because I changed something. So what I'm gonna do? Remember in my stream I wrote down FTL communication. That is faster than light communication, and how that's going to happen is that we are going to delve into the realm of infinite space, infinite frequencies, and infinite time. And I'm not going to explain that. I'm just going to allude to that information, and I'm going to show you. I'm going to put a square wave of 1 kilohertz, and I'm going to watch. You're going to see what happens to the picture. I want you to see this. myself now. As you can see, there are multiple harmonics. In fact, the square wave is the addition of all of its harmonics, whereas the sine wave is only the fundamental, and if there's any other harmonics, they're at a lower level. And what we are going to do is we are going to investigate the area where the square wave goes to its maximum and goes to its minimum. And how we do that is we're going to create a feedback circuit. We're going to analyze the sound when it feeds back onto itself. That sound is going to create noise. However, that noise is going to also contain possibly information from the next, or information from some dimension between, like I don't know exactly between which dimensions. We live in a three-dimensional world. Actually, I can turn this down. We live in a three-dimensional world. So the similar thing between the sine wave and the square wave is that they both travel the same distance. However, the square wave is actually cut off, and it never reaches a peak value. So why is that? It's because that peak value is going into infinity, and then it reappears. In other words, the line between the peak value and the value that goes back down to the negative point, that line right there acts like a wormhole. And that wormhole, it's like, I don't know how to explain it. It's like going from point A to point B almost instantaneously. But it doesn't, because there's a time frame there. And that time frame is it's one half of the sine wave. So if you got a sine wave, it goes up, it goes down, it crosses the 0 dB line, then it goes down and back up again. So there's the top section and the bottom section of the sine wave. I could show you that, but I'm too lazy to do it now. It's getting late and I'm frustrated. That distance between when the sine wave starts and when it ends is called 2 pi. 2 pi radians. If you were to take a circle, cut it in half and flip it, you would have a sine wave, but it's not. It's because I was thinking about this. I'm thinking to myself, why is a circle not a sine wave? A sine wave is more. It goes up at a slope, then it comes down at a slope, and then it goes down, and then it goes back up again. But the circle, it goes in like a circle form, and then it comes down. If you were to just cut it in half and then kind of flip it over, why doesn't a sine wave look like a circle? Is my question. I have a question about that, because it's crazy, because the distance between the beginning of the sine wave and the end of the sine wave is actually the same. Where is my? I want to see, make sure I'm streaming what I'm supposed to be streaming here. So like when I'm talking, you see all kinds of harmonics and shit happening. Well, why is it that a square wave goes the same distance? It's because it's got something to do with like all these harmonics, and the harmonics is what creates your musical instruments. So if you hit a note that sounds like a recorder, which I happen to have one, I'm going to play that recorder, and we're going to see if we can find a 1 kilohertz fundamental and find out where the harmonics are. I'm going to do that right now, as a matter of fact. My recorder broke in half when I put it back up, but we're going to fix that. I got a basic recorder, a recorder has a different sound from just a single harmonic note, a single fundamental. It's got harmonics. So it sounds a little different, and we're going to see what that sounds like right now. We're going to see what it looks like right now. And we're going to find the 1 kilohertz because we know where that is now. So that's pretty close to 1 kilohertz, that note. Wait. The harmonics are actually changing from note to note, which is kind of interesting. I thought the harmonics would be the same, it would just be a different level. There are actually there's like 4 or 5 harmonics off to the right, and they are kind of staying the same. So that's an octave. That's an octave, and I don't know, that's reading about 600 hertz to 1 kilohertz. It's reading a logarithmic graph here. So there's like 4 main harmonics over there. Those harmonics are still there from that octave. So we could create a perfect recorder sound if we discovered those harmonics and added that. I mean, a recorder is a pretty simple sounding instrument, but it's got all that other stuff in there. Further to the right, there's another set of harmonics. And actually, the other 4 next to the first 4 look like they're closer together, and they might be a certain distance, which is the same distance, I think, but they're like halved. Yeah, whatever, there's like 8 harmonics there. There's 4 that are close together, and then there's 4 more after that which are even closer together. So the whole idea, what I'm talking about there is just sampling certain wave sounds, that kind of thing. It's talking about a square wave has all of the harmonics at certain frequencies. If you take the fundamental away from the harmonics, you can do what's called, like in radio communications, you have what's called sidebands. If you, the AM channel, which is audio amplitude modulation, has the sideband, I think it has this, the fundamental frequency, It might be suppressed or something. And then there's lower sideband and upper sideband. Well, that's where your information is. So if we have a square wave, the square wave then it's going to repeat the information in every single fundamental because it's a square wave, but it's a different frequency. It's kind of weird. I mean, that's what the sine waves do. It's just repeating the same thing. But I think it's that idea that the fundamentals, that the harmonics are a certain distance apart. But it's this idea of how does someone do that? So what you do is you create a feedback loop, and that feedback loop bounces back and forth between where the square wave just starts to go up, and then it goes across. It's like that's where that feedback loop is, and it's extremely sensitive. You have to kind of like open up bandwidths and stuff like that. That to me is my idea of where the faster than light communication exists. It exists in that infinite space, and that when we get into that infinite space, then you're actually creating noise. There's noise there. So that's why we're discussing different kinds of noise, and there happens to be on a website. There's white noise that is the same level across octaves. The pink noise is higher level at the higher octaves or something like that. We're going to play some pink noise here in a minute and see what it looks like. If it'll go on from the desktop, because I don't know. Alright, so there's pink noise. Okay, that came through on the desktop. And we didn't change, that level. But you could see the higher frequencies had more power. Let me play that again. I'll turn the mic off. Hello. What's happening there? Where's Reaper? See, with Ableton, I can get the desktop to come on here. Where is... It's Reaper. I gotta have... What if I add another track? And I use... the input as... Just record input audio. Yeah, I don't know. What if I try something? How do I get the desktop to just... Shit. Yeah, it's playing on the desktop. You guys can hear it, but Reaper can't. Where's that? Actually, wait just a minute now. I can fix this. We can run. All right, let me go to my other website, my other computer. And we'll run it from there. And it should be a wiki page, which is We're gonna run off this web page. I'll turn the mic off. It might help to be able to see what we're looking at. This is pink noise from the other computer. Okay, now let's do this. I'm going to pick up some white noise. I'm going to play that. You can see that's not all equal. There's a lot more power on the high end. The pink noise was flat across the band. That's why the audio people use pink noise to set up their mixers. So those two tests worked really good. There's another kind of noise. It's called brown noise. Let's see if we can get that on here. Well, there's actually Brownian noise, but that's not what I'm looking for. Purple noise. It's brown note. What is brown noise? Well, let's just listen to Brownian noise. Brownian noise, supposedly, it's called red noise. Is a type of signal that's produced by Brownian motion, which supposedly is totally random. Yeah, that's got a little bit more, a lot less on the high frequencies and kind of flatter on the low end. What else? That's Brownian noise. Now there's purple noise, which increases 6 dB per octave with increasing frequency. So we know what that's going to sound like. Anyway, noise is all this stuff put together, and you hear this kind of static effect. The trick now is going to be able to play something and see if you can discover it hidden in the noise. Bear with me for a moment. This is going to be this is the last part of my stream tonight, and you will notice something on the display, which is all I have to say. So, there's a signal there, right? And actually, what we can do is we're going to drop this down 3 dB. And now what we're going to do is we're going to go to the website. We're going to grab... I actually like the Brownian noise, but we'll grab the pink noise. And we're going to play this. Alright, so this is the last part of the stream. Just watch what I do. So the problem I've got here is I can't get this narrower enough. Yeah. I also, I'll try something else here. Yeah, that's what the problem is. I can't get the bandwidth narrow enough. There's other types of filters that you can get. Like this is only an equalizer. I don't know what else is in here. My damn headset's acting up again. Hello?
Hello?
That's
That's
actually
actually
feedback,
feedback,
probably
probably
to
to
my
my
mic.
mic.
You
You
know,
know,
for
for
some
some
reason,
reason,
I'm
I'm
not
not
very
very
happy
happy
about
about
what the
what the
computer's
computer's
doing.
doing.
And that other noise is. I don't know what that other noise is. What is that? Is that coming from this connector? Let me disconnect this. No, it's not. I have a buzzing noise in there. I had that problem before with this mixer, and I'm just noticing it now. Maybe it's this other thing here. Wait. No, it's not that either. What the fuck? Is it this? No. Is that mixer grounded? I did unground that. There's a buzz there. I'm going to shut off my stream monitoring programs. We're going to shut all this stuff off. I'm going to call it a night. Um, I think it was a good stream. Like, we're talking about different things regarding noise, harmonics, what my plans are. The next step is going to be how to talk to the computer without me listening to it. I don't know why it's doing that. Let me see something. It's coming across the desktop. It could be because of it's because of Reaper. I used Reaper in order to pick up the audio signal and analyze it, and that worked out pretty good, I guess. We'll save this project as. Um, okay. Hello. Yeah, now you guys can hear me, and Reaper's off. All that good stuff. The only other stuff that I was gonna get into, creating the noise circuits manually. So we have what's called thermal noise. We have resistors. We have this op amps. You run this as inputs to the op amp, and then here they've got DC voltage across that resistor. Um, but just connecting the resistor to the input of an op amp is going to create noise. We could set up things like whetstone bridges to make the input circuit like 1,000 times more sensitive. Um, we need to figure out at what values. Like, I can't. I need to have like I've proven that you can take high pass filter setups, and you can extract information from noise. But there's something else. There's a couple of technologies. One of them is pulse width modulation, which I was trying to get that circuit built. That ain't gonna happen anytime soon because I got too much going on. Um, Pulse width modulation takes amplitude and frequencies and puts them out at varying frequencies at a constant output level. There's that, which I believe was an idea of collecting audio information. However, there's something else. There's a game called, well, I can't remember the game, but you can take audio sound files and put them through what's called a waterfall. And what that does, it takes samples of all of the noise at certain instances. And if there's harmonics in that noise that come up ever so subtly, you can see those harmonics, and you can even set things up to create pictures using noise. Now, when we get into doing feedback loops, audio feedback loops, and things like that, we're going to create a noise system that we have to be able to regulate it. We got to be able to stabilize it. It's extremely sensitive. It probably has to be in certain lab type environments, that kind of thing. But I think I want to run that noise into a wave file like Audacity. No, Gold Wave has that program. I got that program. That's got a waterfall setup, and there might be some other programs that's out there. Um, so that's the idea behind what my stream was all about. How does that relate to music? Um, I wanted to do samples, and I wanted to create. There's just with some of the other instruments, there are just so many subtle harmonics that make the instrument what it is. Um, I can try that on another stream. I don't think it's going to make a difference because I wanted to recreate some of the piano sounds that's on a program and put it on my synthesizer. So that was where I was going with all of that. There's that aspect. There's the waterfall sound, and then there's the pulse width modulation setup, which um, I was using polarized information. So there's x and y axis, and there's the z axis, which, well, axis not a z axis, but there's the t axis, which is time. So you have an electromagnetic um, field, and as that field travels through time, one of the axes is electrical information that goes around in a circle. The other one is magnetic information, and you can separate those by using, with light waves, you can separate it with a polarizer. With electricity, you're just measuring the max amount of electricity or the max amount of magnetism in a circuit. And my thinking was that coming up with the information from the noise was more magnetic than electrical. Um, I don't know because like electrical, like I got a bunch of magnets and stuff, and I wanted to create something that could pick up magnetic interference through a very sensitive circuit, like a coil. And this would have to be down into the millivolts range. That can be done. And I want to set up a whetstone bridge circuit. I've got a huge wire wound resistor that's a certain value, it's like 30K. We're going to set that up with a whetstone bridge with another resistor that's 30K to balance the circuit, but um, there's going to be imbalances. It's because you got to match impedance. So we're going to have an impedance whetstone bridge that is perfectly balanced, and we're going to use the large resistor as an antenna to pick up noise in certain areas. And I'm not going to discuss where those areas are, um, but I can explain to you that there are areas of esoteric energy accumulation. Let's put it that way. This is the alien technology that I'm alluding to in the title of my stream. If you've listened to me for this long, which most people probably haven't, you will never pick up on this information, which is pretty much my intent, because I'm going to release information that I have gleaned from my own head. This is not anything coming from any any special place or anything like that. It is information that is um, in my own brain. It's not. It is coming from. It's live information that I get. I have access to, but it's not. It's esoteric information. It's not literal physical information that you can see or hear or anything like that. It's like I'm a medium, and I pick up these signals and messages, and that's the extent of that business. That's where I'm going with that, and it's abstract information that I'm learning to put in physical form of transducers and that sort of thing. So you've got thermal noise that you have to deal with. We set this up. We set it up in the form of a type of antenna, and that antenna, which is the inductive coil resistor, is going to be located near in such a way that it's going to have access to a magnetic field. That magnetic field is extremely, extremely strong, so that the very slightest variation of that field, the slightest change in that magnetic field, is going to be picked up by that resistor. So the trick then is how to amplify the magnetic field to make it even more sensitive. Um, you might think, well, why not just amplify changes in the magnetic field? The changes in the magnetic field happen. I mean, if they were to happen quickly, there is no equipment that can measure the change in magnetic field quick enough. You'd have to have the other option is to look for changes in electrical fields, which you can do with FETs, which is called field effect transistors. And I was doing some studies with that, and that's how I discovered what I believed was a pulse width modulated signal coming from a source that was not supposed to be there. Okay, and I'm not kidding you. I swear on my life here that the setup that I had set up gave me the idea of collecting noise from different polarities, canceling those noise signals, which is the next thing. You get the two noise inputs, you cancel those, and what you're supposed to have left is your final output. That's the whole story right there. So one signal is the noise, the other signal is the noise plus the signal. You put them two together, you cancel the noise, and out pops the signal. Yeah. Well, you've got to have references to go by. So um, if we can have a noise setup in a differential amplifier type circuit or a comparator circuit of some sort, it's actually two op amps, one running positive, the other one running negative, which in turn, and the other two positive and negative sides of the op amps are connected together, and one positive is the noise, the other negative is the noise in the signal. Theoretically, the noise cancels. Theoretically, because it's the same noise. Then you've got a phase. There's going to be phase differences. So we got to take into account a phase circuit between the time it takes from the noise to go from one input. Well, you know, that's the whole idea. I wish I could draw this out. I want to draw this out. Let me see. Where's my I did this once before. You wait just a minute here. Maybe I can. I might be able to do this without my computer getting discombobulated. Let's see. Let's just do it this way. Wait, new BMP. Open with paint. And I'm just going to bring this down like this. I'm going to do this really quick, I hope. And then we're going to, let's see, black. How do I fill this in? Okay. And then we go to here. And we're going to add, that's a program. Properties. We're going to use paint. And then we'll just go ahead and resize this so we don't have to see all this other garbage. I have knowledge, and the world is not ready for the knowledge that I know. So if I take, what is this? I don't know how this triangle shit works. I'm just going to do it freehand. We'll use this large one. We'll use, let's use orange. So we got 2 op amps. Oh shit, that doesn't work. This is supposed to be black. This one's supposed to be orange. And so we got 2 op amps. Okay, so we got this. Is that coming out on the screen? Yes. And let me just do this really quick because I got rid of the other one. Now, this is not the exact circuit. I wouldn't divulge the exact circuit anyway, but so we've got plus, minus, plus, and minus. Then we've got a blue signal. Let's make purple boxes here. Oh, that's a little bit large. And then we'll make a blue box down here. And we'll take the green signal is going to be, this is the S plus N, and it's going to go through a circuit. Let's see, it's kind of greenish. Well, we'll just put it green. Okay. And we make an X in here. This is a circuit. Then out of this comes, well, not necessarily anything. It goes into the minus. Now, between the plus and the minus, generally, you know, maybe there's like a resistor here. Generally speaking, there's other things that happen here. Now up here, we could take the yellow. I just used yellow. Let's use dark red. So you got this one. And you got this, and then this goes into here. And this is the noise, which is actually equal to N. So then you've got, let's make this, then you've got another box, and you've got outputs. Maybe you got an output coming to here. You may have another output coming to here, and then you've got an output coming to here, and supposedly this is just your signal. You got plus and minus. The noise should cancel, and the signal now is riding on this negative thing here. So we talked about a phase relationship between the two noise signals. So let's say we make a circle, we put another, well, we could just put it like a sine wave. We could send this in here, and then like this would go down here like that. This is a signal here, and then we've got um, what if we had a circle here, and then we run this back through some kind of a circuit, and then this goes around and over and up here. This is the control line. So what happens is this would be a test signal. So this is CL for control line, and this is a test signal. We just call it TS. And this is a phase. So this is going to be plus, like this. And this one down here, it's going to be like this. Okay, but there's going to be a phase difference. So if we run a test signal through both of our input sources, we can make sure that the phase is accurate, and we can do this by sending a control circuit back to this test signal, or wait just a second here. No, that's not right. That's not right. Where's my eraser? We don't want that. We want the control line. The control line probably goes to here. And then it readjusts this phase. And we could put another arrow here. We just put this arrow, and then we put another arrow like this. It's not very good arrows, but that's a phase adjuster. And we set that up for a signal. We use a test signal to calibrate this. We set this up so we know for a fact that everything is perfectly in phase, even though it's 180 degrees out of phase, because if it's not in phase, then that's going to add noise. And the whole purpose of this is try to get rid of the noise. This is my idea. And yeah, I should probably save that. Let's see, we'll just save it as those are this PC pictures. We could save it as phase circuit. Let me see that again. Yeah. Let's save that as a phase circuit. That's something I wanted to do. That's really the priority of my project right there, is to do that. Once I get that circuit built, Then I have the challenge of creating the transducer, which my first idea, because I picked up this resistor, this wire wound resistor, and I want to see how sensitive it is to magnetic field changes. Um, the only problem with that, I think I should use, like, I don't know, it was free, like I didn't have to pay, I paid a couple dollars for it. I'm thinking what I need to use is a coil with umpteen amounts of turns on it, very thin wire to monitor magnetic field changes, and it has to be a high response. It's got to be into the audio response field because that's the only way information is going to get delivered. Now, if we were to use a magnetic field as a source for this information in infinite space and time, um, I forgot where I was going with that. When you have a laser, you have reflective mirrors that bounce the light back and forth to create an infinite field, which is another idea. I'm going to use light too. I'm going to work on light experiments with all this. So, but with magnets, how would you create a bouncing magnetic field that reflects back onto itself? So if you have two magnets that are either attracting or repelling each other, there's something happening between those magnets. So, but the only problem there is that you've got a strong magnetic field, and it's going to be very difficult for anything in other dimensions to be able to move that extremely strong magnetic field. Um, you can put wires around a coil, and then if the magnetic field moves, it generates electricity. Um, I think a detector is a better method rather than direct. I don't know why I'm going with this detector method. I don't think, because there's what's called the BH curve, and the curves, there's like, it's not quick enough to sense the change in magnetic field. I think it has to be a weak magnetic field. I got my eyes closed. I'm thinking, I'm trying to collect this information in how I'm going to proceed with this transducer setup. Um, if there's a weak magnetic field, it may not go into the next dimension. It may not be strong enough. So, how do you create a magnetic field? How would you create, let's see if we can look this up. Creating a magnetic feedback loop. Strong and stable magnetic levitation. I don't know what that is. Building for a small maglev system. Magnetic levitation. Wow, why are we getting anti-gravity? Do it yourself at home. What is that? Are we looking at this on the website? Because this should be up on my stream, which I believe it is. Looking at web page. It's not quite centered, is it? I don't know what this is. Don't put a lot of faith into these YouTube videos, okay? Because half of them are scams. That magnet that he's got is extremely powerful. You can get pinched with those. Those are called, there's a certain name for them. I forgot what it's called. I don't have those magnets. That's a small one. This is kind of the idea I wanted to build for an earthquake detector. All he's doing, what the hell is he doing? He's just holding the thing up with the magnetic field. What the hell is that supposed to be? Oh yeah, that's just total BS. What the hell is that supposed to be? Where's the comments? I did this with my car, now it flies. He's using the grass as a grass screen, so moving it if it's being like it's fuzzy in the background. See, like I said, don't pay any attention to that shit. Um, what do we got here? I don't know why. Oh, now look, they're talking about pulse width modulated system signal adjusts the average current in the solenoid, which controls magnetic field. Well, that's fine, but that's not related to what I was talking about earlier. Levitated object. That's really not levitation. It's just using a magnetic field to lift the object in the air. We don't want to do that. We want a feedback loop, like a laser, like you know what I'm saying? Connectors and signal. I don't want that. Level strong and stable magnetic levitation. More garbage. Whoops, what's down here? So that's just wire that he bought. I've got a coil of wire like that, but it's thinner. That's why I'm thinking of using that coil. Yeah, I don't know what he's doing there. Avoid feedback stabilization. Yeah, see, they're just talking about using magnets, and that's not what we're looking for. That's why it's not in there. This is a difficult thing. Um, with lasers, you can have a feedback loop. The feedback loop is what allows you to enter chaotic space, which is going to create noise, and that noise that's created is a result of what the noise is in that location, in that field. And that field could be accessed directly through a wormhole. Like the wormhole is there, it's already there. All we need to do is create um, the correct field in order to access the wormhole, which essentially is just the beginning and end of zero time. There's a time factor that's zero. If you if you do 1 over t, frequency is in hertz, it's cycles per second. It's the number of cycles per second. So if you take out time and set it to zero, the frequency and the time is inversely proportional. So the frequency goes way up. If the time goes to zero, the frequency goes way up. That means that's basically how a square. So how is a square wave made? How does the square wave know when to stop and go straight across to the next section? Is my question. A square wave is the total of crap loads of harmonics. It just adds those harmonics together. But you could keep adding harmonics infinitely, and you would never make a you could never make a perfect square wave. So a square wave is eventually it's clipped off. It's just cut in half at the top and the bottom, and you got a square wave. Well, yes and no. And my my study involves that point where it goes up and across that very small area right there. I don't know why I'm thinking about this, because the other ideas were, like I said before, it was X and Y polarization of electric and or magnetic fields. I don't know how to polarize receptors for magnetic fields. Magnetic fields is a north and a south. Um, I mean, there must be a way to do it. And then the other problem is trying to build up a magnetic field and have it feedback on in itself. Like if you have a coil and then the voltage just keeps going up and up and up, you get static electricity, and the static hits the ground, and then it kind of like recycles. Yeah, that's my destiny. And did you get all that in a nutshell? Good luck, home.